are the people? Turn on the light. Okay. So let's calculate the scattering amplitude. Okay, so let me tell you what we have done in the last lecture. So we have this incident A. Okay, psi incident. We have solved this equation. Lambda square A square acting on psi incident. We have found the form of psi incident. What is that? Okay, psi incident. We have found it. Okay, so that's our EKZ, e raised power IKZ. It's our plane wave, and we have figured its expansion in terms of the spherical harmonics. Clear?
Yes, sir.
Okay. So that's like infinity to this 1 I raised power L JL, where JL is the spherical Bessel function. Okay. Okay. So this is actually in R, because we are interested in the asymptotic limit. Okay. R tends to infinity. So the JL is actually signed by, okay, it's a sine function. Clear? It's something. L is 2L plus 1. This we have already done in the last lecture, but let me write it here. So it is sine of KR minus L pi by 2, okay, divided by KR and divided by PL cosine. Call this as equation 1. Okay. Then we have solved this equation. Okay, so now we consider the potential. Okay, turn on the potential. So your potential is like this. So you have twice m by extra square E minus V of R. Okay, again you are having a psi that's equal to 0. Clear? So what is this psi? This is the asymptotic wave function. This psi is actually, okay, psi incident plus e raised power I k r by r f of theta phi. Clear? So we are figuring out what is the asymptotic form of this psi by solving the Schrodinger equation. Okay, got it? Okay, since I have told you in the last lecture that we are assuming our V of r goes to 0 as r tends to infinity. Clear? So in that way, if this goes to 0, it is essentially the same equation. Okay, so but it will have a phase shift. Okay, phase change on the waves. Got it? Okay, so now let's write that. So I will have this psi when r tends to infinity. Okay, so what is the form? Anybody? It is the same form. Clear? So okay, so when V of r, okay, so we are actually in the asymptotic limit. It goes to 0 as r tends to infinity. That means essentially it is the same equation. Clear? The solution is same. Okay, except, so let me write it as, okay, L equal to 0 to infinity. Let me introduce some normalization constant which we don't know. Okay, which we have to figure out. Let's call that as AL. Then it will be 2L plus 1 I raised power L. And the form will be same thing except the change in phase. KR minus L pi by 2. So let's write a phase change in the by delta L. Clear? Okay. So by KR, and you are having this PL cosine. Got it? Got it? It is actually the outgoing. If you see the sine KR by R, it's the outgoing spherical wave. Clear? Sine KR by R. It's up. If you take, actually it is the imaginary part of this series or IKR by R. It is the outgoing spherical wave. Okay, so the wave effect comes from here. So that's why I introduce in this wave actually this delta L. Got it? Samajh aa? So now let's substitute it in that very formula. So this is what we have done already. Okay, so what is unknown to us? So we have figured out what is the form of psi in the asymptotic region. Okay, that means getting the effect of the potential. Okay, so that is this very psi, and we have also figured out psi incident. And what I need to figure out now, f theta phi. Okay, so let's substitute. Okay, so let's call this as equation second. So I can write now. So okay, so we have this e raised to I k r by r f of theta phi. So that's equal to this psi minus psi incident. Can I write it? So why psi is which? It is asymptotic wave function. It takes into account everything. Okay. So now let's write these things. So that is the subtraction of the two. So let's write it. So it is L equal to 0 to infinity. Okay. So I'll write 2L plus 1 I raised for L PL cosine of theta by KR. It's common to both terms, is it? So you are having these terms. So what is only different? Sine. Clear? And this AL. Okay, so you are having AL sine of KR minus L pi by 2 plus delta L minus sine of KR minus L pi by 2. Okay, everybody? Agreed? Clear?
Yes, sir.
Okay, so let's simplify this a little bit. Let's put it in the form of exponentials. Okay, so then I can figure out this area. So I can write it this object as so e raised power I k r okay minus L pi by 2 plus delta L minus e raised power minus I kr minus L pi by 2 plus delta I divided by 1. So it is this thing. Okay. Similarly, what this will be? So it is e raised power I kr minus L pi by 2 minus e raised power minus I kr minus L pi by divided by 2. Clear? Okay, so what I will do, now look here. So you are having e raised power I kr minus L pi by 2 in this very factor. E raised power I kr minus L pi by 2 here. Got it?
Yes, sir.
So sure? So let's put it in this way. So I am having e raised power I kr by r f of theta phi. It's equal to L equal to 0 to infinity 2L plus 1 I raised power L by kr, and you are having PL cosine theta. Okay, so let's separate out these terms. So the first term is anybody? So it is something AL e raised power I delta L. Clear? Now look here. What I am taking. So you are having AL e raised power I delta L. Then minus. You don't have delta L term here, is it? So minus 1. So what is that? And you are multiplying here e raised power I kr minus L pi by 2. Got it? Everybody? So there is one, okay, 2I is in the denominator, right? Okay, so let me put it in a moment. Then what you are having the other term? What is the other term? Plus? Okay, so minus and minus plus. So let me take minus out. Then you are having AL e raised power minus I delta L. Clear?
Yes, sir.
So AL e raised power minus I delta with a minus sign. Clear? So it is minus and minus is plus because I have taken minus out. So it is minus 1. Got it? Then what you are having here? E raised power minus I kr minus L pi by 2. Got it? So and there is a in the denominator there is actually 2I. So let me write it. Okay? Everybody?
Yes, sir.
Any problem? Okay, so now the point is here. Now look here, if you see okay, forget about this pi by 2. So it is e raised for I k r divided by k r. Clear? So what that is? It is a spherical wave, but it is outgoing wave. But if you look at this, which is e raised for minus I k r by k r, it's a spherical wave, but incoming wave. Clear? Or ingoing wave. It is okay. So you are having here two types of waves. Okay, or you can reproduce two types of boundary conditions. The one boundary condition that you are having only the outgoing wave, okay, outgoing spherical wave, because once you do the scattering, okay, after the scattering, the wave will move as a spherical wave, okay, it will move outwards, clear? But there can be also the possibility wave can move what? Inwards, okay, but we are interested in the boundary condition where wave moves what? Outwards, okay, because on the left hand side here, I am having only which wave? Outgoing wave. So that I am interested only in the outgoing wave on the right hand side. Okay? Okay, so we consider the boundary condition here. To reproduce outgoing spherical wave. Okay? Got it? Got it? So that means the coefficient of this ingoing spherical wave, it should be 0. Okay, so which implies coefficient of ingoing spherical wave vanish. So that is, so you are having AL, E is for minus I delta L minus 1 equal to 0. It implies AL e raised for minus I delta L is equal to 1. So what it gives me? AL is equal to e raised for I. Clear? So we have figured out the value of AL. Okay? Got it? Since, okay, so AL is what? Okay, so this term is now 0. True? So where I will put AL now? Here. So let's substitute. Okay, so therefore I am having e raised for I k r by r f of theta phi is equal to summation L equal to 0 to infinity 2L plus 1 I raised for L P L cosine of theta, and there is this kr, okay, and okay, so let's write it. So what is our AL now? E raised for I, so it is e raised for twice I delta L minus 1 divided by 2I and e raised for I k. Okay, so let me write it this way. E raised for I k r, e raised for minus I L pi by 2. Can I write it? Huh? Okay, good. Everybody? Okay. So this I, now, okay. So what you are having? E raised for I k r on this side, e raised for I k r by k r by r. Clear? Got it? So what have we got? So we have got f of theta phi. So what is that equal to? L equal to 0 to infinity. Since k is a number, you don't have, let's put it outside. 1 by k, L equal to 0 to infinity, 2 L plus 1. So you are having I raised for L, E L cosine of theta, okay? E raised for twice I delta L minus 1 divided by 2I. Then you are in e raised for minus I L pi by. So this is our scattering amplitude. F of theta represents scattering amplitude. Clear? Okay. So okay. So now let's look at this I. So I is actually e raised for I pi by 2 gives you I. Got it? But it is having a power L. So it will be simply raised power L. Okay. So it is e raised for I pi L by 2, and you are having here what? E raised for minus. So that means this, okay, this object multiplied by this object is equal to 1. Clear? Okay. So what remains? So which implies theta phi. So that's equal to 1 by k, L equal to 0 to infinity, 2L plus 1, PL cosine of theta e raised to twice I delta L minus 1, okay, by 2I. Okay, so it's your scattering potential. Got it? Okay? Any problem? Okay, so let's calculate now the scattering cross section, rather the total scattering cross section. Yes? Now if you see, what is the phase change? So it is e raised to twice I delta L. Okay, so this term represents your phase change. Yeah? So the phase change effect is here, huh? In this very term. Huh? Okay. So let's try. So we usually write a total scattering cross section like this. Eh? So total scattering cross section. Okay. So we write it as d omega. It is a solid angle, and d sigma by d omega. Clear? So this is the total scattering cross section. What is our d sigma by d omega? It's actually f of theta phi. Okay. So now you see there is no phi dependence. Is there a phi dependence in that? So you can put simply f of theta. Clear? Okay. So I need to calculate what? The magnitude of this thing, magnitude square. Huh? Everybody followed it? Yes. Okay, good. So now let's write it. So what is d omega? So it is 0 to 2 pi d phi. Okay, then you are having 0 to pi d theta sine theta. That is our solid angle. Yes. Now let's take f of mod of f of theta square. That means it is f star multiplied by f. Clear? So let's take that. So 1 by k summation L equal to 0 to infinity 2L plus 1. Okay, PL cosine of theta. So since I am okay, so let me write e raised to twice I delta L minus 1 divided by 2I. Clear? So let's take, this is 1 f of theta. Since I have to take mod square, that means multiply it by the complex conjugate. Huh? Okay, take the complex conjugate. Okay, multiply it by, okay, 1 by k. Since L is a dummy variable here, so I will not use L. So let me write some L prime is equal to 0. So twice L prime plus 1 P L prime. So it is like this in cosine of theta e raised to twice I delta L prime divided by 2I. Clear? So now this is f star multiplied by f. Okay, so that's your mod of f square. Okay, so now let's take this star. So when you take the star, so this value will change. This will become minus. Clear? And this will become minus. Okay, so this is your f star. Okay, so now let's multiply. Okay, is there any phi dependence? No. So let's integrate over phi, that is equal to 2 pi. So you are having 2 pi, then you are having integration. Okay, so let me write, okay, so let's put 0 to pi d theta sine of theta, then you are having summation L equal to 0 to infinity, summation L prime equal to 0 to infinity, then what you are having 2L plus 1 PL cosine of theta, then you are having 2L prime plus 1 PL prime cosine of theta. Got it? So let's multiply now these exponentials. So then you are having e raised power minus twice I delta L minus 1 divided by 2 minus 2I, okay, into e raised power twice I delta L minus 1 divided by 2. Clear? Got it? Any question? Huh? So there is 1 by k square. 1 by k square is also there. Okay, so now let's look at this thing. You are having 0 to pi. Only this term and this term depends on theta. Okay, so let's use this very identity. 0 to pi d theta sine theta PL cosine of theta PL prime cosine of theta. What is that equal to? 2 by 2L prime plus 1 delta LL prime. Clear? Everybody followed it? Okay. So therefore I can write this sigma total, that's equal to 2 pi by k square. Okay. Summation of L equal to 0 to infinity. Summation of L prime equal to 0 to infinity. You are having 2L plus 1. Okay. 2L prime plus 1. Then you are having out of these things 2 by 2L prime plus 1 delta L prime. Then you are having this factor. Okay, so 2 into 2, it's plus 2, it is 4. So let's put it as e raised power minus twice I delta. It is L prime. Minus 1 into e raised power twice I delta L prime minus 1 by 4. Clear? So now let's sum over L prime. Once you sum over L prime will be replaced by L. Okay? So 2 multiplied 2, that's 4, that will cancel with that 4. Clear? Okay? Clear? Okay, so now let me cancel many factors here. So look here, when you sum over L prime will be replaced by L. So what it comes? It becomes 2L plus 1. So that means 2L plus 1 cancels out. Got it? So what remains there? So it remains simply 1 by k square, summation L equal to 0 to infinity. So it is simple 2L plus 1. Okay. So now let's multiply. Since L prime is now same as L, so it will be something. Okay. E raised power minus I theta, e raised power plus I, it is 1. Minus 1, that's plus 1. Minus, it's e raised power now minus I. So it will be simply twice cosine of 2 delta L. Clear? Okay. Everybody got it? Huh? Where is pi? Oh yes, here. So it is pi here. Okay? Okay, good. So now let's take 2 out. So it is 1 minus cosine of 2 delta L. It will be simply twice sine square. 2 multiplied by 2, that's 4. It is simply equal to 4 pi by k square, summation of L equal to 0 to infinity, 2L plus 1 sine square delta L. So this is your total scattering cross section. Now total scattering cross section. Okay. So if you know what is the phase shift of a given wave, clear? Yes, better. Any problem? Okay. So if you know the phase shift, because L is what? Your angular momentum component, clear? So if you know your phase shifted delta L, you know actually the total scattering cross section. Clear? Got it? So what are the values of L? So it is actually an infinite sum. So what are the values of L? It goes from 0, 1, 2, 3, so on. Clear? So if you have, let's say, if there is only one term contributing in this very sum, let's say only L equal to 0 is contributing. So that means you are getting a total scattering cross section due to L equal to 0 states, or the scattering is happening in L equal to 0 region. Clear? So we call that as an S wave scattering, because L equal to 0 means S wave. So if you are having L equal to 1, that means P wave. So similarly, L equal to 2, that means D wave. Got it? Okay. So there is a corollary to this result. Let's look at in the forward direction. But result we will interpret later on, that result there. So let's look at this thing. So what is our f of theta? So what is this f of theta? We wrote, because it's independent of what? Okay, phi. It's 1 by k summation of L equal to 0 to infinity, 2L plus 1 PL cosine of theta, and e raised power I delta L minus 1 divided by 2I. So it is twice. Okay? So this is our f of theta. Clear? So since, okay, so let me put the result what we are trying to do. Let's put it this way. Suppose if you are having some incoming flux, what should be the outgoing flux? So, no, I mean, so the total flux should be conserved. Clear? So let's say if you are having a beam of incoming particles, so you should get actually the resultant flux should be same. So in accordance with the incoming flux. In other words, the current should be conserved. Probability the incoming current should balance the outgoing current. Let's take theta equal to 0 direction. Theta equal to 0. That means in the forward direction of a scatter. Clear? So what happens? So have you seen, let's say, no, not 180 degree. Let's say if you are having some object. So let's look at, suppose this is an incident wave, clear? And I am looking in the forward direction. Theta equal to 0. Okay? Got it? So this is your K and this is your K prime, clear? And the theta is now 0 because both vectors are in the same direction, clear? Okay. So have you seen there in this very region, in the forward region, there is actually some shadow occurring? Suppose classically thinking, have you seen a scattering of an object? Huh? So you know, suppose scattering of an object, let's take a pen. You throw a light, what will happen? There is a shadow is forming. Why? That shadow is only in the forward direction, is it? Shadow is not in this very direction. What is the reason? Think in terms of waves. Yes, there is actually the scattering. So it means what is happening? Since this scattering beam contains both incoming beam and what has been scattered, the outgoing spherical waves. Let's say here it will be cylindrical waves, and they will actually overlap in such a way they will form. Actually, they will have a destructive interference. Okay, because of destructive interference, you are having a shadow in the forward direction. Clear? So that means in the theta equal to 0 direction, you always have a shadow. Thinking classically, clear? A generalization of this result to the quantum mechanics. Okay, we call those as the optical theorems. Optical theorems gives you what is this amount of scattering going in the forward direction. Okay, so because this the forward direction scattering is contributed by the destructive interference. Okay, if there is no, let's say if you are having a shadow, let's say in the forward direction, what will happen? So the flux that should go actually in the forward direction, it should adjust in the other directions. Clear? Yes. So you should be having this way flux, and this way. Clear? The reflection. So this is actually the conservation of the probabilities, or the conservation of sinus intensity, or the flux conservation means actually the conservation of the probabilities. Got it? So that is the result of what we are trying to look at. Let's look at the theta equal to 0 direction. Okay? Got it? So if you see, look here, look at this formula itself. You are having this f of theta contains the contribution from, so you are having -1 here, is it? So it is PL cosine of theta. You can think it as your usual incident wave. Clear? And there is actually a phase shift as well. So that is the scattered wave. Clear? So that means this f of theta contains actually the superposition of what? Both incident as well as the scattered wave. You can look at the form of psi itself. So when you wrote psi like this way, is equal to psi incident plus e raised for I k r by r, okay, f of theta. So calculate f of theta from here. It's actually superposition of these two waves. The scattered wave which contains the entire information, got it, plus the incident wave. Okay, so that's why there can be actually the constructive inference as well as the destructive inference. Okay. Okay, so let's take this f of theta equal to 0. So it's, so we'll calculate it quantitatively, this theta, when we will do the Eichner approximation. There I will show you how these shadows arise. Okay, so let's take PL. Okay, so what is PL cosine of 0? So that's equal to 1 because it is simply PL of 1. So that's 1. Clear? PL of cos theta. Okay. Okay. Yes, is it correct? Huh? Is it correct? Okay. PL of 1 is always 1. How? What is the formula?
1 divided by x dot L summation.
Huh? Just look at the formula, you will see it is always equal to 1. Okay, so what remains there? E raised of twice. Let me write it this way. Okay, so you are having I, let me put it as minus, okay, so it is twice k here. Let me put as minus I upwards. So what comes here? So it is cosine of twice delta L plus I sine of twice delta L minus 1. Clear? So can I write it? Huh? Exponential, I have put it in this way. Okay, so now let's write the imaginary part. Imaginary of f of theta equal to 0. So what is that equal to? Let's take the imaginary part. So it's minus, okay, minus 1 by 2k summation of L equal to 0 to infinity 2L plus 1 cosine of twice delta L minus 1. So that's our imaginary part. Clear? So now tell me what is 1 minus cosine of twice delta L? So it is actually minus twice sine square delta L minus 2. So it will cancel minus and minus. So it's 1 divided by k summation of L equal to 0 to infinity twice L plus 1 sine square delta L. If you see the what is the formula? So can I write it like this way? So let's write it as k by 4 pi. So that means I am multiplying by k by 4 pi. What it will be here? 4 pi by k square. So 4 pi by k square summation of L equal to 0 to infinity twice L plus 1 sine square delta L. What is this objective? It is scattering cross section. Total scattering cross section. Okay? So in other words, what you have, so the total scattering cross section in the forward direction, you can calculate it by this way. So 4 pi by k, okay, imaginary of. So we call this is a content of the optical therapy. So I will do it in detail later on. Huh? So it is a quick corollary of this very result. Yeah? Got it? Okay. Okay, so now let's discuss what kind of problems we will be doing here. Eh? So memorize this formula. You should memorize it. Eh? So let's take, okay, so we are actually interested low energy phenomena. In low energy scattering. Clear? So when you are having a low energy scattering, so that means there will be only few terms in this extension they will be contributing. Okay? Particularly we will be interested in actually only L equal to 0 case. Okay? So we will be considering only the S-ray scattering. So I will give the prescription of what to do. Huh? So now look here. Suppose if you are having a given problem and you need to figure out your first time in the class. Huh? That one. You are from this department? No. Just. So you are here for the first time. कहाँ से आ रहे हो? हाँ? लेट क्यों हुआ? क्या हाँ? कोई एप्लीकेशन डाली थी? प्रिस्क्रिप्शन है कोई? Okay. So what I was saying, so we'll be discussing actually. So S-wave scattering, that means L equal to 0 case. Okay. So now let's take this thing. So you are having total scattering cross section, only the one term. So it is simply equal to 4 pi by k square sine square, okay, delta 0. Clear? Because L equal to 0. So what it means? So or I can write it like this way. Okay, let's write this. Okay, so let's define delta as this delta 0. So our total scattering cross section at low energies, it's equal to 4 pi by k square sine square delta. Now, okay, so let's look at this very formula. Suppose in a given problem, what you need to figure out then? So if you try to figure out what is the cross section of a given problem, okay, given scattering at low energy, what you need to figure out? You need to figure out what? The phase shifted delta. Clear? Got it? How you do it? You have to solve the Schrodinger equation, okay, for that very potential problem. Clear? Samajh aaya? Okay. So let's give first the prescription. I mean, when you can say the low energy case. Okay. So let me give. Suppose, so this very case will be considering the low energy scattering, okay, with short range interactions. I should say with short range interactions. Okay, so let's go to the formulas, the Schrodinger equations. There you can actually figure out what I mean by that. Okay. So you have this equation d2ul by dr2, which we have written already, plus k square minus l into l plus 1 by r square into ul is equal to 0. I have not considered here potential because if I am in the asymptotic domain, potential vanishes. Clear? Got it? So it is of no use to put the potential term here explicitly. So that means this equation is valid for both the cases, in the asymptotic region and in the incident region. Okay? Got it? Okay. So now if this thing happens, if the potential, let's try, if the potential is such that you adjust potential in such a way such that it becomes negligible, okay, for, okay, let's say if you are tuning your potential in such a way for a given scattering problem such that your potential becomes negligible. Okay, so let's, okay, for what kind of condition I mean to say, this r square, okay, you can take, let's take this k square out. Okay, so if I take this k square out, what remains here? 1. So you are having k square, what is here? K r square. Clear? So it means if there is no impact of the potential here, it means this term should be very small. Clear? So then it is essentially actually a free particle equation. That means I don't have any effect of L on my waves, on my partial waves. Clear? Samajh? So it means this r square, okay, so that we write this kr square is larger than this L into L plus 1. Clear? So that means then it would have very little influence. So which the potential have very little influence on components of wave functions. Components of wave function is all the L values with such angular momentum. Clear? Okay. So that means potential will not have any kind of effect. So this is a very important condition. Now if I am having this kind, okay, so let's assume range of potential is R0. Okay. So assume R0 as the range of potential. What does that mean? So you are having influence of potential only up to what? R0, up to certain distance. Okay. So now let's calculate what are the number of phase shifts. Okay. So let's calculate the number of phase shifts. Okay. So that is clear from this very formula. The number of phase shifts. So in that case, they should be actually equal, huh? Okay. Okay. So let me write it. Then maybe it will be apparent. Okay. So the number of phase shifts, how many will contribute in this very formula? Okay. Phase shifts. Although we will be only interested in the S wave, huh? Phase shift is that will influence the scattering. Okay. In any given case, can be okay, like this thing. Eh? If you are having now k r naught square, okay, that is something greater or equal to L, not large, but it can be like this thing. Eh? Samajh aaye? Okay. So okay, so if this is very large, so if this region is very large, I should put if this is very large, then you don't have any kind of effect. Clear? But if they are comparable at certain at which point at the range of the potential, clear? So that means there is actually the contribution of the L. So much, okay. So we are on, okay. So I have told you. So because we are in the low energy scattering and the short range interactions, only L equal to 0 term will contribute. Okay. Okay. So I will take an example. But in case of the Coulomb potential is actually the long range interaction. If I take the low energy scattering of the Coulomb potential, then it's not necessarily only S equal to 0 will contribute. It's actually the superposition of the many different waves. So that's actually very complicated problem. If time permits, I will show you that problem. Okay, so let's go to the example first, then maybe you will understand what I am saying. Okay. So let's take the neutron-proton scattering. Low energy scattering, neutron proton. How much time is remaining?
10:40.
Okay, so let's calculate only first the values, then we'll solve it. Okay, so I will assume, so I'm considering only the low energy scattering, not the high energy. Low energy means, so typical values, we will see how much low is. Okay. So let's assume our potential is modular. First, we need to consider the potential or the interaction between two these particles, how you model them. Because when you consider the scattering, you should know what is the interaction governing the scattering. Okay, so that we model by a potential. Okay, so let's assume the potential are the okay, through which this neutron and proton are interacting with each other is governed by like this thing, spherical potential well. Spherical potential step, like this thing. It is in 3 dimensions we are constrained. So I am saying it's V of R, it's like this thing, and attractive potential step for R less than A, and it's 0 R greater than A. So what it means, so you are having a potential step like this thing. So you can think this R as this A as a range. So let's take this as an R, okay? This is your A, this is what? 0 naught, and this is your minus V. It's not actually a rectangular box. It's what? It's actually a sphere. Got it? But a step, a finite sphere you can think. So within up to that radius, your potential is what? V naught. Okay, beyond that potential. Okay, beyond that point, it is 0. So that means A is the range of what? Potential. Clear? Okay. So let's assume. Okay. So in this case, by the way, if I consider this kind of problem, at a low energy, so this R naught, so that's actually here A, it's typically, so since I am in the discussion, I have said R naught is the range, okay, so that is A here, it's of the order of 2 Fermi, Okay, so it's like this 2 into 10 raised power minus 13 centimeter. So that's equal to 2 Fermi. Fermi means it's Fermi. So it is 10 raised power minus 15 meter. Clear? Got it? Okay. So now let's consider okay, so consider a neutron, okay, of energy. So I will consider only the neutron. So think proton is at rest and the neutron is coming with certain energy, clear? And it's scattering with the proton, considering this kind of potential, okay? So they generate this kind of potential. You can think within the, let's say, neutron you are having. So one proton and one neutron, what is that object called? Deuteron, is it? Okay, so you can think we are modeling that kind of, object, okay? So let's consider the energy of 1 MeV, neutron energy 1 MeV, clear? So incident on a stationary proton, okay? So what is the, so that in center of mass of the system, the neutron will have, so in the center of mass, neutron will have energy of the order of 0.5 MeV. What is the center of mass? Because neutron and proton we consider of the same masses. What is the center of mass? It is half. Clear? Okay, good. Okay, so this leads to. So now let's calculate the momentum. What is the momentum? So that's actually root of twice m e. Clear? Because e is equal to p square by 2m. So I am having the kinetic energy of the neutron because I am considering only the neutron is in motion, right? And proton is stationary. Okay, so let's calculate it. So can I write it as 1 by c root of twice mc square e, because I know the energy I have written in terms of what MeV is. So that is in the mc square units. So how much is that? So it's 1 by c root of 2 into how much is this thing? MC, it is MeV. So so it's 10 raised power 3, okay, into what is E? It's half, because E is what? The energy in the center of mass, clear? So mc square is the rest mass, you can think of. Okay, so it's half. How much is that? So it is of the order of 30 MeV c square. Okay, so it is very trivial. So let's calculate the wave vector. Wave vector is P by H cross. So what is P? 30. So it's not c square, it is c. Okay, so it is 30, okay, MeV by H cross c. Okay, H cross at c. So it is of the order of 10 raised power 12 centimeter inverse. Because wave vector is having length inverse units. Okay, so now let's write this k square. Okay, so k square r naught square, how much is that equal to? So that's the same thing as k square a square here. So it's equal to, what is k? It's 10 raised power 12. And what is a? It is 10 raised power minus 13 kind of thing. So it is 2 into 10 raised power minus 13 whole square. So that's of the order of 2 into 10 raised power minus 1 square. Clear? Got it? So much more? So you have to plug in the factors yourself. So it's very less than 2. So much more? So what is the condition? What was the condition? So you are having the condition k r naught square. So it should be okay. So since this is less than 1, L cannot be less than 0. Clear? So what is the possible value? L has to be equal to 0. So much more, because then equality will follow. So much more? Okay. So that means I have to consider only the S wave scattering in this very problem. Now let's say if you don't have the numerical values at hand, so when you choose whether I should go for the low energy or not. So if the problem is specified, it is a low energy problem, just use low energy phenomena, and in that case you just put this Ka is less than 1. Okay? While A is the range of the potential, K is the wave vector. Okay, so if this product is less than 1, then you use always the S wave scattering. Clear? Unless and until specified. Huh? Clear? Okay, so we'll calculate the scattering cross section of this problem tomorrow. Okay, so time is up. Huh?